Hello everyone, this is lecture 63. We'll introduce two new concepts, impedance and admittance. You've learned the two concepts in lecture 62. In order to differ from the real coefficient algebraic relationship between the voltage and the current on the resistor, we've introduced the imaginary coefficient algebraic relationship between the voltage and the current on the inductor and define this part as the inductive reactance. Resistance and reactance both have block function to the current. By combining them together, that is, combining the real and the imaginary number together, we get a complex number. It's called the impedance. Admittance is dual to impedance. They are key contents of this lecture. Let's analyze this one-port circuit. It contains RLC and dependent sources. The whole circuit is operating in SSS. For this circuit, we can use the method of solving the current with given voltage or solving the voltage with given current to get that U equals what times I. Inside the one-port circuit, the characteristic of resistor is U equals R times I. The characteristic of inductor is U equals J omega L times I. And the characteristic of a capacitor is U equals minus J times 1 over omega C times I. After the transformations, this part should be a complex number. We define it as Z, that is impedance. The impedance often has a real part and imaginary part. Its real part is called resistance. Its imaginary part is called the reactance. It can also be written as a form of modulus and a phase angle. The modulus is called the modulus of the impedance. The phase angle is called the angle of the impedance. So we can draw the triangle of the impedance. It's like this. The triangle shows the relationship between the expression of real and imaginary parts and the expression of modulus and phase angle. It's easy to understand. Let's take this RLC serial circuit as an example to explain the impedance characteristic of the one-port network. From the figure, we know that Z equals R plus J omega L minus J times 1 over omega C. And it equals R plus J times omega L minus 1 over omega C. We can write it as a form of modulus and angle. This phase angle has different conditions when L and C have different values. In the first condition, omega L is larger than 1 over omega C, so phi is larger than 0, and U leads I. In this condition, we call the circuit is inductive. So the circuit expresses not only the characteristic of the resistor, but also the characteristic of the inductor, not pure inductor, so it's called inductive. In the second condition, omega L is less than 1 over omega C, so phi is less than 0, and I leads U. In this condition, the circuit shows capacitive characteristic. The third condition is special, in which omega L equals 1 over omega C, so phi equals 0, and the voltage and the current are in phase. This special condition is called resonance. We will discuss resonance in detail in the following lectures. Next, let's draw the phasors of all variables in the one-port network. Suppose the current phasor is like this. According to the UI relationship of the resistor, UR and I are in phase. Which is the larger one depends on if the resistance is larger than 1 or not. We are not concerned about this now. For inductors, U leads I 90 degrees. So UL is in this direction. For capacitors, U lags I 90 degrees, so UC is in this direction. The port voltage U equals UR plus UL plus UC. So we should add the three voltage phasor together. By applying the parallelogram law of the vector addition, we can get the voltage phasor. But in circuit course, we are accustomed to the method of joining them head to tail. It's like this. We draw the current phasor. The horizontal phasor is called the reference phasor. After the current phasor, we draw UR. Then UL. UL is vertical upwards. The starting point of UL is at the origin point in the left figure. Now we draw its starting point at the end of UR by joining them head to tail. It's like this. Similarly, U equals UR plus UL plus UC. So we draw the start point of UC at the end of UL. It's like this. Then we get the phasor U directly. By comparison, you will find the method of head to tail is simpler and clearer. So you should be familiar with this method. This graph is called the phasor graph. Phasor graph is an effective tool for solving SSS circuit, so you must understand and grasp it. We've drawn the condition when omega L is larger than omega C. When omega L is less than omega C, the phasor graph is like this. When omega L equals omega C, the phasor graph is like this. The value of UL and UC depends on RLC. In SS circuits, we can often find that the value of some branch variable, such as UL or UC, is larger than the value of the port voltage. This condition doesn't exist in resistive circuits. Let's see an experiment about this. This is a serial RLC circuit. Let's observe its SSS phenomenon. The input is sinusoidal signal on board, and the output is the capacitor voltage. Channel 1 of the virtual scope connects to the input signal, and channel 2 connects to the output. Let's look at the waveform on the scope. The yellow one is the input waveform. The green one is the output form. This experiment shows that in SS circuit, the response of capacitor voltage is a sinusoid voltage at the same frequency, and the amplitude of capacitor voltage is a little larger than that of the input voltage. This is a characteristic of dynamic circuits. We've introduced the triangle of impedance in the previous page, and it shows the relationship among Rx and the modulus of Z and theta and phi. For this circuit, this part is called UR, and this part is called UX. It has been seen both in the phasor graph of inductive and capacitive circuits. According to such a definition on branch variables, we can draw the phasor graph UR, UX, and U. This graph implies that the circuit is inductive. U leads UR theta degrees, phi degrees, sorry. So these two triangles are similar.